Hi, let us continue with our discussion with AC analysis for BJT small signal. Okay, so last time we have discussed the two types of models that we can use. So we can use the RE model or the hybrid model, although we have seen the relationship between the two, so they are just almost the same. Okay, so they just differ in the names of the parameters. So in this topic, we will be concentrating more on the solution for the whole circuit. Okay, so the solution for the whole circuit itself. So the contents are the common emitter fixed bias configuration, and then we have the voltage divider bias, we have the common emitter bias, and then we have the emitter follower configuration. So the emitter follower configuration is our common collector configuration. So the only common collector circuit that we have. And then we have the common base configuration. And then we have the collector feedback. Collector feedback is also common emitter. So fixed bias, voltage divider, common emitter bias, and then the collector feedback configurations, all of them belongs to the common emitter configuration. And then we have the hybrid equivalent circuit and model. Okay, so to start with, we have here the, excuse me. So we have here the common emitter fixed bias configuration. So the input is being applied. So the input is being applied at the base of the transistor, while its output is at the collector of the transistor. So common emitter is characterized as having high input impedance compared to common base. Why high input impedance? Because its common emitter Zi is equivalent to beta multiplied by Re compared to common base, which is just equivalent to Re. Okay, so and low output impedance with a both high current gain and voltage gain. Okay? So, we have here removing the DC effects of your VCC and by shorting your capacitors. So this is your common emitter fixed bias configuration, and then replacing them by its RE model. So its RE model is in the blue box. So you have your beta RE, we have the current source, which is beta IB. So in some books, they make use of the triangle instead of the circle. Okay, so if you in the circuit analysis subject, usually the triangle is for variable and the circle is for a fixed value, right? If you can still remember. So what is included in the transistor itself is the input impedance of the transistor, which is beta RE, the current source, and your RO here. Okay, so what are the steps? You still have to determine your beta, your RE, and your RO. So beta and RO, usually they are given in the specification sheets for the transistor, or test the transistor using a curve tracer. So RE, we solve for RE using 26 millivolts divided by IE, but we still need to calculate your RE using our DC analysis for the value of your IE. Okay? So these are the different formulas that we have. So Zi is equivalent to RB parallel your beta RE. Okay? But when your RB is greater than or equal to 10 times your beta RE, the input impedance is just approximately equal to beta RE. So for the output impedance, we have here RO in parallel with your RC, but when your RO is greater than or equal to 10 times your RC, your ZO is approximately equal to your RC. So here are the formulas for common base. For the current gain calculations, So your VO is RC parallel RO divided by RE. But when RO, is very, very large, so the parallel combination nears the value of your RC, therefore making your voltage gain minus RC all over RE. So every time you use common emitter configuration, always remember that your voltage gain is negative. That means it is 100, the output is 180 degrees out of phase with its input. So for the current gain, we have used this formula. I have shown you this formula when we used the equations early, the example from the previous video. So that will give you AI, which is approximately equal to beta. So we can also solve your current gain from your voltage gain, and that is given by negative AV ZI, the input impedance, divided by RC. So as you can see, our AV is negative, so we have your negative times negative, that will give you a positive current gain answer. Okay, so where this came from, so we have here the the derivations. So just read and understand the derivations. Anyway, I have included here step by step derivation, so I'm sure you can follow this one. Okay, so for the current gain, so the current gain is determined by applying the current divider rule to the input and the output circuit. Okay, so that gives you approximately equal to beta, or we can use this equation too. So negative AV multiplied by ZI times RC. So for fixed bias configuration common emitter, the phase relationship between input and output is 180 degrees. So the negative sign used in the voltage gain formula indicates the inversion. So voltage divider bias configuration. So this is your model. So the only difference is your R1 and your R2 here. So we call this R1 and R2 R prime. So you still need to determine your beta, RE, and RO. So beta and RO is usually found in the specification sheets, while RE, we usually solve this, you usually derive this using your DC analysis. So you have to solve for IE first. Okay, so the difference here is your parallel combination of your R1 and R2. So in this case, your input impedance, which is R1 parallel R2, so your ZI is R1 parallel beta RE, or simply R1 parallel R2 parallel beta RE. So the output impedance, no problem, it is the same with the fixed bias configuration, nothing changed at the output side. So for the voltage gain, it is also the same, and for the current gain. So what did we notice here? In the DC analysis, we said that among the different configuration, we do not want the fixed bias configuration, because it is among the four different types of common emitter, it is the most unstable, while the voltage divider is the most stable. But by looking at their AC portion, okay, at the AC analysis, we can see that the voltage divider performance is just like the performance of the fixed bias. Technically, by looking at the formula for their voltage gain and their current gain, they are just the same. Okay, so that means that both both fixed bias and voltage divider in the AC analysis portion, they are likewise, we can say that they are just the same. So the performance of the fixed bias is just the same as with the performance of the voltage divider. How much the voltage divider can amplify has the same amplification that the fixed bias can do. So the difference really lies on the DC analysis, because in the DC analysis, we can say that your fixed bias is not stable. We do not want an unstable circuit for your amplifier. That's why, although they can perform the same, they can give the same amount of amplification, but still we choose the voltage divider because we have established from the DC analysis that voltage divider is much more stable compared with the fixed bias configuration. Okay, but in the AC portion they are just the same. So here are the what do you call this, derivations. Okay, so they are just the same, and since the current gain is very similar to the common emitter fixed bias configuration in except for the for the R prime, so the current gain will give the us the same format. Okay, so phase relationship the same. Why? Because they are both common emitter, so all common emitter configuration shares the same phase relationship. So there are two ways that we can what do you call this, we can have an approach with the emitter stabilized configuration. We have the unbypassed RE. Look at what happens in the unbypassed RE. We don't have a what? We don't have a capacitor here. So what happens when we don't have a capacitor there? So when we draw the RE model, we didn't remove your RE here. So since RE was not removed, we have a much more complicated formulas and equations. For the Z, we have an additional parameter here, which is ZB, because this time beta RE is no longer your ZI. Okay, but rather you have the inclusion of your RE here, wherein the current which flows across your RE is beta plus 1 multiplied by your IB. So do you still remember that in our DC analysis, what we see in the input side is no longer just RE, but RE multiplied by your beta. So the resistance or the impedance being shown at the input side is not just the value of RE, but it was amplified by the value of your beta here. Therefore, you have the base impedance, which is the sum of your RE plus your RE here multiplied by your beta. Okay, so once your ZB is established, your ZI now here is the parallel combination of your RB and your ZB. Okay, so since small RE is very small compared with the big RE, we can have your ZB, which is equivalent to beta multiplied by the capital RE or the emitter resistance. Okay, so those with smaller cap, lower cap letters, they are your AC parameters. You don't borrow them from the laboratory and then place them in your circuit. Usually it is within the transistor itself. Okay, so at the output side, since we are opening your current here, so no effect whatsoever. Therefore, for the output impedance, it is just equal to your RC. So the only impedance that is shown at the output is your RC. So here are the derivations. So if you can kindly understand the derivation. So it is given step by step. So I don't think there will be a problem in deriving for the formulas. Okay. So for the voltage gain, as you can see, it becomes negative RC all over RE. Take note, it is RE with the capital letter. So usually it is in terms of kilo ohms, while RE is in terms of ohms only. So the effect really is lowering. There is still an amplification, but it is very low compared with the one with a bypassed capacitor. Okay, so the formula for current gain and the formula for the current gain from your voltage gain. Okay, so here are the derivation. Kindly look for the derivation so that if you suddenly forgot about the formula, you can always derive. Okay, so the phase relationship is still the same. Why? Because it is still under common emitter configuration. Okay, when it comes to bypass, so what do we mean by bypass? We just place your bypass capacitor here. And if this happens, the effect of your RE here is removed. So when this is removed, the circuit is just like the fixed bias configuration. So all of these three, fixed bias, emitter stabilized, and the voltage divider, once their RE is removed, they share the same formulas. Okay, so they share the same gain formula, they share the same current gain formula, voltage gain formula. They are just the same. So for the emitter follower configuration, what is the difference here, class? So the difference here is that your output is being taken at the emitter terminal. So the difference between the emitter follower is that your output is taken at the emitter, while the common emitter configuration outputs are taken at the collector. Although both has an input taken at the being inputted at the base. Okay? So for emitter follower, so you may recognize this as the common collector configuration. Indeed, they are the same circuit. Note that the input is on the base while the output is from the emitter. So why is it called emitter? So this is the formula. So we we do not bypass your RE here. Why? Because it is where your output is being taken. So we cannot bypass your RE here. So just the same as with the unbypassed capacitor earlier or the unbypassed RE earlier, we still have to solve for ZB. Okay, so we need to solve for ZB, and then your ZI, so same ZB, so your ZB is equivalent to approximately equal to beta RE, and then your ZI is equal to RB parallel your ZB. Okay, so for the current gain, for the output impedance, so your ZO is RE parallel your RE, smaller letter RE. So ZO is approximately RE. So for emitter follower configuration, it is characterized as low output impedance. So common emitter configurations, they are high output impedance, while common collector or emitter follower configurations, they have a low output impedance. So for the current gain and the voltage gain, look, for the voltage gain, approximately equal to 1 or usually lower than 1, because look, the denominator is always greater than the denominator is always greater than your numerator. That's why common emitter follower or common collectors are not usually being used as an amplifier. Why? Because their voltage gain is lesser than 1. So technically, it's not an amplifier. Okay? And also, absence of a negative sign, that means the input is approximately is directly or in phase with its output. Okay? So the phase relationship, although this is quite wrong because the output must be lower than the input, but it shows that they have the same phase. Okay, no phase shift between the input and the output. So among the three, common base, common collector, and common emitter, only common emitter has a 180 degrees phase reversal. Both the common base and the common collector, they have no phase shift between the inputs and the outputs. So this is your common base configuration. So the input is applied at the emitter while the output is applied at the collector. So as you can see, base is, base is common to both the input and the output. So the common base is characterized as having low input impedance. So why low input impedance? So ZI for common base is only RE. Okay, unlike for common emitter, it's beta RE. Okay, so high output impedance with a current gain less than 1 and a very high voltage gain. So this is the RE model. Look, you have here your RE only, not beta RE. So we can only see beta RE if we have a common emitter configuration. And your current is alpha IE. Okay, so it's pointing upward. That's why we have a negative sign in the current gain for a common base configuration. So you will be needing alpha and RE. So both are alpha can be seen in the specification sheets, while RE you need to solve for your IE first using DC analysis. Okay? So Zi is RE, emitter resistance in parallel with your RE here, and your ZO is equal to RC. So for the voltage gain, this is approximately equal to RC all over RC. The only difference is the negative sign. Okay, so the absence of the negative sign here means that we have no phase reversal. And of course, the current gain is approximately equal to -1 or negative alpha. There is a phase reversal between the output current and the input current. Okay, so here are the derivations, very simple. So phase relationship for common base, it has no phase shift between your input and your output. So the collector DC feedback configuration, the network has a DC feedback transistor for increased stability, yet your capacitor C3 will shift the portions of the feedback resistance to the input and the output sections. So the feedback resistance can also be shown at the output sections. So the portion of your RF shifted to the input or output side will determine by the desired AC input and the output resistance levels. Okay, so for the input impedance, you have RFI, parallel beta RE. So why beta RE? Why this one? Because this is still under common emitter configuration. Okay, and for the output, it is the parallel combination of your RC, RF2, and your RO. So in cases wherein RO is not given or RO is very, very high, this leads to the parallel combination of RF2 and your collector resistance. Okay? So here are the derivations. Okay? So the important thing is you solve for the value for your current gain. So as you can see, the formula for the current gain is just like the same formula that we had, and also for the voltage gain. So the only difference is the parallel combination of RF2 and your RC. Okay? So for approximate hybrid equivalent circuit, so H parameters can be derived from the RE model. So the H parameters are also found in the specification sheet for your transistor. Okay? So approximate common emitter configuration. So this will be a great help in your SIT work from the previous video. So you have the hybrid equivalent model versus the RE equivalent model. They usually look the same. So they actually look the same. The only difference are their names, the names of their parameters. Okay? So approximate common base configuration. So for hybrid equivalent model and the RE equivalent model. So troubleshooting, check the DC bias voltages. If not correct, check power supply. Check the resistors, check the transistor. Also check to ensure that the coupling capacitor between amplifier stages is okay. So check also the AC voltages. If not correct, check transistor, capacitors, and the loading effect of the next. So the amplifier stages and the loading effects will be discussed in electronics too. So practical applications, audio mixer. So you have preamplifiers. Usually preamplifiers, they are being used to couple or to match impedances. Okay, so that will also be taken in electronics too. Random noise generator and sound modulated light source. Okay, so that concludes our topic for bipolar junction transistor. Okay, so the next videos, if the COVID-19 will still not be solved, so the next videos will be about field effect transistors. So just like in BJT, we will be discussing field effect transistors introduction first, and then its DC analysis, and then we proceed to its AC analysis. Okay, so have a good day. Don't forget to pray. Okay, don't forget to pray. Stay safe at home, and if you don't have anything to do, you just read your textbook, and you just watch the video. If you have any questions, you just try you just message me, just send me a message if you have any questions so that I can answer them. Okay, so have a nice day and God bless. Bye.